in solving systems of linear equations. So today we'll see a couple of examples using the Gauss Seidel technique, and then we'll start with the interpolation. So we'll start to talk about a new topic, and we'll see how much we'll do regarding the interpolation. But let's start first with where we left. So Gauss Seidel interpolation, it's used, we use it mainly for the linear systems of equations, okay? And linear systems of equations, we just assume a coefficient matrix which can be written like this. Ax, this is equal to b, okay? So this is how we start. But in terms of when we solve systems of equations, the systems of equations, they are not always linear. Okay, so sometimes we might expect some non-linearity terms in x. Okay, we're going to see a couple of examples regarding these, and in that case, we could have, let's assume here the terms can be x squared sine x y squared. Okay, imagine for a moment that now we don't have x and y as unknowns. But we can have a serial of non-linear terms that might appear. Of course, this is not the best way to represent it, because the equation can be as random as 3x squared minus sine x plus logarithm of y. This is 3, and then we would have the other one, it's 2 tangent x minus 3y. This is equal to 2. Okay, so imagine now this system is not, for sure it's a nonlinear system, okay, that's the first thing we can say, but we have to be a little careful if we design a possible solution for such a system. So this can be considered just, we can roughly denote this one as a function f1, and this would be roughly another function that we need to solve of f2, and the way that we can represent, or the way that the best intuitive approach that we can think about when we solve this problem is to plot these graphs and see where they intersect, okay? Because these are nonlinear systems and are a little more complex. But we'll come to these problems. Let me raise this one a little later. And last time, I think we stopped at the Gauss Seidel method, which had, it was very similar to the Jacobi method. Now, if you remember, the Jacobi method, whenever we were finding out a solution, not a solution, whenever we find out a new value for the x1, x2, and x3, or xyz, in Jacobi method, we used to keep the old value, but in the Gauss Seidel method, we used to update the numbers right away. So, last time we stopped the recordings of the class while we gave for some exercises for all of us, and in these exercises you were expected to solve them. And as a beginning of the class, I would kindly ask you if you could enter a 1 in the comment section, as assuming that this is an attendance sheet. Okay. So if you enter 1 in the, okay, thank you very much, so it started. So it will help me to keep track of your presence. And let's see. So last time we gave a couple of examples, and let's try to solve one actually. It's always good to start like this. So let's imagine that we have this equation, minus 8 x1 plus x2 minus 2x3, this is equal to minus 20. 2x1 minus 6x2 minus x3, this is equal to minus 38. So this is the second equation. Then we get minus 3x1 minus x2 plus 7x3. This is equal to minus 34. Okay, so here we have three equations, and then we want to solve these. For sure, they are linear equations, and we want to solve these using the Gauss Seidel method. Now, a good start, it would be the following. So we can start here with 0, 0, 0. Okay? So we can insert initially all zeros. And then we need to figure out what are the iterative equations that we're going to use. So the first one, we know that all these equations are written like this, like x1 is equal to 1 over a11, and on the other side we have b1 minus a12 x2 minus a13 x3, right? So this is the general expression that we generally use, which in this case it will be the following: x1, the new value of x1 would be equal to 1 over minus 8, okay? 1 over minus 8. Then we have, if we look at the first equation, we have minus 20 minus x2 plus 2x3. So this would be the first equation. Now, having this, we are going then to. So for x2 and x3, we can immediately assume that these values will be substituted with zeros, okay? Because the initial value, that's what they are, and the answer will be minus 20 over minus 8, so we get something like 2.5. Okay? So then here we get a 2.5. We go to the second equation. And in the second equation for x2, we have x2 is equal to, so we pick out the x2 from here, x2 is equal to 1 over minus 6, its coefficient, times, we have minus 38 minus 2x1. Now x1 is 2.5, okay? This value that we found here, we immediately insert it here. Then we get plus x3, but x3 is still 0. So we get here a 0. And if we do the calculations, we get something like 7.17. And then the x3, we read it from this equation. And x3, this is 7.17. Then the x3 would be equal to 1 over 7. Okay, so this is the coefficient that we get here. And then we take all these terms to the other side. We get minus 34 plus 3x1 plus 3. And x1 is 2.5 plus x2, where x2, the new value of x2 is this. So this is minus x2 on this side, then we get the plus x2 on the other side, and finally, so this is what we get after the first run of using the Gauss Seidel method. So then this is the first iteration. Now probably the first thing that we need to do here is to calculate what is the error. And the error, it compares how much change we have from the new value with respect to the old value, but assuming that the new value is a true error. Okay, so which means the following. So the error, it will be calculated like 2.5 minus 0. This is absolute value over 2.5 times 100%. Now, starting with the initial value as 0, probably this doesn't make much sense for the moment. So let's have a look. We can have a look at the second iteration. So once we apply the second iteration, let's see what we get. So here, x2, we have to insert 7.17. We read those values from there. So this is minus x2, 7.2. Let me do it like this. x3 is minus 2.8. I'm going to write the approximate value here, minus 2.8. Then the value that we get here for x1 is going to be 4.08. And so on. This 4.08 we can immediately, or let's write it 4.1. Then here we get plus x3. This x3 is minus 2.76 with a minus sign. Okay, and the next value we get 8.15. So this 8.15 as x2, this will immediately go to this value. And this 4.08, this will update this value here, which is for the x1. This will be 4.08. And the final answer for the x3, it will be the minus 1.94. Minus 1.94. So this will be the updated values, and then probably we need to have another iteration because the errors we have quite a considerable amount of error. And in order to calculate the respective errors, you know how we do this. We are going to calculate for each of them. So, for example, if we consider this, I guess we are clear on this one. But the error in this case, it would be the absolute value 1.94 minus 1.94 minus 2.76. Over, this is plus, so this is minus 2.76 over minus 1.94 times 100%. So once we do this, we can calculate this value, and we get something 2.76. This is approximately 2.84 divided by something around 2. So this is approximately, what do we get here? No, 2.76 minus this. This is 0.84 divided by 2. So we get something like 0.4 times 100%. This is approximately 40% error. So we get something like 40% error in this for this iteration. Now we continue like this, and let's see. So the error here is approximately 40%. We have to calculate the error also in the other two elements. And so when we change from 7 to 8.15, and so the respective errors, if we write the errors in red, this is around 42%. For the second value, we get 12.13%. 12.13% for the second value, and for the first value, we get 39%. So it looks like we have a decrease, and we need to check this one with the third iteration because we can even run the risk of not having the system converging. Now, if we look, we can have this issue. So sometimes the problems they might not converge, or the Gauss method might not converge. And regarding this, we can check actually if the system is diagonally dominant. Can I have any comment from you? Is the system diagonally dominant or not? What would be your answer?
Yes, it is.
Okay, it is because we observe that the diagonal terms, they are larger than the sum of the other elements. So this minus 8, the absolute value of minus 8 is 8, is larger than 3, what we see here. And this 6 is larger than the sum of the other two terms, and this other one is also larger. So this problem, it should converge, which means that we have some hope. But if we continue again by substituting the values, we should converge. And let me see the values here. It looks like with the third iteration, these values go down to 2 to 3%. Okay, I'm just going to write this one, just the results of the next iteration. So after the next one, we will get something like 4.004. The next one is 7.99 and minus 1.99. So these values with respect, the error from these values to these, it's something from 2 to 3%. So that's how much error will be in this iterative method. Now, this is how Gauss Seidel method is. Okay, so probably we can look at another example again, and let me see how fast we could, to see how the convergence moves on. We could also try to formulate this problem, but by writing this one on. I'm thinking if we can. Yes, probably I can try to do this one a little later by offering a new method that we can do this fast. Let's see another example. If we have time, we can try to solve this one okay, since we are a little strict on time, let's move on with a different example. So overall, this is how the Gauss Seidel technique is. Now, we said that these equations that we are solving, they were linear. Okay. Now the problem is that sometimes the equations that we have to deal, they are not linear, and in this case we have a huge challenge. And for this part, that use this part of the board. So let's assume that we have a function f1 which depends on x1, x2 up to xn. Okay, now this is equal to 0. We can have another function f2 which depends on x1, x2, and xn, and this is also equal to 0. And we can have several like these. And as we wrote before on the board, this can also include nonlinear terms. Now, in order to solve this problem, what we try to do, now we know that we want to find the root, right? It's not that we're trying to find the root, but we're trying to find let me think for a moment. Let me correct myself. So far, the problems that we were solving, there were systems of unknowns, which look like this. Ax is equal to b, okay? And this were solving any type of problems that had coefficients like these. Now, nonlinear terms include sine of x, okay? Logarithmic of y, and all of these. And now, the same system of equations, but linear, we can reformulate a system of equations that is not linear in such a form, and finding x, which was in this formulation. In this case, if we write it like this, it will be equivalent to finding the value for x for which the functions are 0. Okay, so this is equivalent. I'm correcting myself with what I said before a while. This is equivalent to finding the root of a function. So if you remember, we used to have so in the previous chapter, we were dealing with finding the roots where we use different techniques such as Newton-Raphson second method, and other techniques. And now we will solve systems of equations, but non-linear, reformulating them as if we're trying to find the roots in such a form, okay? And one of the best techniques to do this one would be the Newton-Raphson. Now, what was the best thing, or how, if you remember, how did we start to solve the Newton-Raphson technique? We did the Taylor series expansion. Okay, so we were trying to find the Taylor series expansion, and this includes something like this. So now the function f is a function of x. Okay, so any function, since here this depends on x1, x2 up to xn, this function, it depends on x, and we can do a Taylor series expansion like this. We can say that f, so let's have a look of what we've written on the board. We always know that, I'm going to erase this one very soon. We know that, again, a small reminder, the Taylor series expansion always assumes that we are going to evaluate the function in proximity of some x0 using all the values of the function and the derivatives of the function evaluated at x0. Okay? Pra Taylor series expansion këtë punë bën. Jep një vlerë një pikë të caktuar referencë, dhe mundohemi të gjejmë vlerën e funksionit në pika tjera, në këtë pikën këtu, ose në këtë pikën këtu, ose në këtë pikën këtu, duke përdorur vlerën e funksionit të x0, derivatin e parë të funksionit të x0, derivatin e dytë të funksionit të x0 e kështu me radhë. Pra kjo është esenca se si e gjejmë, se si e përdorim Taylor series expansion. Tani, when we try to find the roots, we always assume that x0 is a root, and then we try to move away with some value delta x. Okay? But now, x is not a number that we had in functions that we were trying to find the root. Now, x is a vector. Okay? It's a little more tricky, but it's not difficult. Okay? We'll try to make this one as much intuitive as possible. So here, we have f of x plus delta x. If we write the Taylor expansion, this will be equal to f of x, and probably, I think it's best if we write this one fi, because if you see here, we can have several functions, and in order to make this one a little clearer, as we move on, let's assume that the first function, or let's try to find an example that we might solve soon. Let's assume that we have this function like this. X squared plus y squared minus 3, this is equal to 0. And the other function is xy minus 1, this is 0. Okay, so here we get two functions. Now, this is f1, okay, and this is f2. So f1 is a function that x squared plus y squared minus 3 is equal to 0, and the function f2 is xy minus 1 is equal to 0. If we write it like this, we are as if we're really trying to find the root of this and the root of this. But now, when we're trying to solve a system, what is the essence of trying to solve this system? Now, these two functions that are on the board, let's have a look first how they would look if we try to so the first function, it was first of all, we have this x squared plus y squared, this is equal to 3. Now this function, it is like, it's a square, sorry, it's not a square, it's a circle with radius 3. So we can try the following, x is equal to, I prepared something, probably I have it here. X in space. Sorry, this is, yeah. Okay, I think I can pick up this one. The square root of 3 is around 1.7. So let's write this here. So this is x, and this is the x is from minus square root of 3 up to square root of 3, and then we can find, using this x, we can find x1, and we can define also x2. Normalisht, ne dim që rrethi, po të ndërtojmë një rreth dhe po ta plotësojmë, ai nuk është funksion, sepse funksion është kur për çdo vlerë të x-it ne kemi vetëm një vlerë të y-it. Në këtë rast, kur të ndërtojmë një rreth, atëherë i takon që, let me pick it out immediately from here. So this is half of the function, and
question mark.
Okay, we have a mistake here. So y2 is minus. Okay, so what we see in the graph, I was just trying to plot actually the x squared plus y squared is equal to 3. But since we're trying to find the root, we just rewrote this function. Let me write it here, x squared plus y squared is equal to 3. It doesn't make sense in MATLAB, but I'm just trying to make it visual for all of us. And now, similarly, we can also define a couple of functions that look like this. Where did I start them? Okay, that's x3 and x4. And let's find y3 is equal to 1 divided by x3. And y4 is equal to 1 divided by x4. Ajo që po mundohemi të bëjmë është thjesht të plotësojmë fakt këtë. This is not correct.
Question mark.
And so finally, these two functions, the first function, it was the equation of a circle with radius 3. Good. The second function, it was x times y is equal to 1. So we draw on the same figure these two functions, and apparently it's from the graph, we see that the solution of this system of equations, which is not linear, unlike what we did with the matrix notations, the solution will be at the intersection of these points, okay? So it looks like this system has 4 possible solutions. So that's what we're trying to do, okay? Just that these equations which are seen here and also in the slide, to make it kind of easy, we just also plotted them here. So if we are to solve this, that's where we should be looking for the solution. And now we want to, so let me switch back to the blackboard. So these were these two functions, which are shown here on the board. And in order to consider the Taylor series expansion of this function, we can write that fi, where I, let's assume for a moment, ia është një numër që shkon nga 1 te 2, sepse kemi dy funksione. So I, it goes from 1 to 2, at least for this case, and this function itself, if it is evaluated at any vector x. Now, what is a vector x? A vector x can be, which in this case is the x and y, it can be a pair of numbers. So we saw that these two functions, there was a circle with radius 3, and this function y is equal to 1 over x. Now, the first function is anything which can be where we can enter any pair of numbers that satisfy this equation. Now let's remember how was the Newton-Raphson method when you had a single function. We used to write something like this. We said that y y is equal to y0 plus dy over dx, right? So this is how we used to find the Newton-Raphson solution. And let me see if we have it. So this is what we did for a single value. Now this is what we are going to do if we have a vector notation. Okay, so this is the first order approximation of the Taylor series expansion of a function. Okay, and these functions, now a series of functions, these functions, they all depend on different values of x and y. And now what we observe from here, in fact, let's see what we get. For this specific case, since we have two functions, we can construct the following. We have I is a number from 1 to 2, and j is a number from 1 to 2. And it looks like, since we have pairs of two numbers, we are going to have a matrix which is 2 by 2 matrix, okay? And this 2 by 2 matrix, it will look like this. We'll have so let's set I is equal to 1, and j is going to change over the 2. So here, in this matrix, we will have the derivative of f1 with respect to x, okay? And then we'll have the derivative of f1 with respect to y, okay? So this is how we're going to construct the first part. And when we get the other value for I, when I is equal to 2, we'll get the derivative of f2 with respect to x, and the derivative of f2 with respect to y, okay? So this is what we're going to acquire, okay? So we will see, we'll get the 2 by 2 matrix to represent the derivative of a function. Now, this matrix is called the Jacobi Matrix. Okay, now let's see how we're going to deal with this. First of all, we have this x is a vector, plus delta x, which means that if we are going to solve this system, how do we do this? We always assume an initial, a possible solution. For example, if you look at this graph, which we were showing before a moment, but we erased it. So we had a circle with radius 3 intersecting with a line which was y is equal to 1 over x. Now, a possible root can be anything between 0.5 and 1, okay? So we can insert this initial x0. This can be, we can start with iterative techniques from 0.5 to 1.5, right? This is the initial value. And then the delta x change, it can be something like adding a delta x, which is 0.01, okay? And this is 0.01. So this will be the delta x. So this is the x0, and this would be plus the delta x that we will iteratively change. Okay? And here we write the following. We say fx plus delta x. This will be equal to the f of x as a vector plus the Jacobi matrix here, and this is a matrix. It looks like this, times delta x. Delta x is a vector. Okay, so we know linear algebra, we know how to modify this, and let's see how we're going to work with this one. Now, and probably let's write also, so having this in mind, let's see what the steps that we're going to use will be. So first, to solve this system, again, while we keep an eye on the first thing that we do, we estimate an initial x. So we assign an x0, assuming that this could be a possible root, probably after we look at the graph of the function. That's the first step. Then the second step, it is to insert this value in this function to check whether it's true or not. Okay, so we evaluate this one, fx0. Okay, that's the second step. The third step is to identify, we need to find the Jacobi matrix. So we need to find this Jacobi matrix, which is the respective derivative of the first function with respect to x, which is just 2x. Okay? And the derivative of this function f1 with respect to y, which is 2y. And then we will have to take the derivative of this with respect to x, which will be y, and the derivative with respect to y, which will be x, because we know how the derivative of a simple function looks like. So we find this, and then we should find delta x. So we need to estimate what the delta x will be. So if we start from a value of 0.5 and 1.5, how much should we assign for the change in these two values? So to this vector, we will have to add another vector, but this is infinitesimal vector, right? Small values with respect to these. Now, to find the delta x, so this is the fourth step. Now, let's have a look for a moment in this equation. So this is something which we need to look at this one carefully. Since we're trying to find the root of this function, let's assume that we are going to add a delta x, and this change in delta x will make this 0. Okay? So let's assume that this fx plus delta x, this whole thing, this is, let me use a different color. So let's assume that now this is 0 is equal to f of x plus the Jacobi matrix x delta x. Okay? So hoping that this will be 0, we can write this equation. If we write this equation like this, that means that, let's do this here, that means that if this is equal to 0, we can have the following. Jacobi of this matrix X, but this one itself is a matrix, right? Because the Jacobi are these four derivatives which are plotted in a matrix form times delta x. This is equal to minus f of x. Okay. Now, if you look at this system, what this really is, this is an equation. So this is an equation that looks like this: a times x. This is equal to b. Now, we are very good at calculating these types of equations, right? But at the same time, let's have a look again. Where this function, we are going to equal this to 0, assuming that a small change of delta x will make this 0. And probably it's not always true, but this is an iterative technique, so we keep improving it. We write this equal to 0, we get this, and then this function f of x 0 that we found in step 2, we will insert it here. And this Jacobi matrix that we found in step 3, that's why we do these steps, we insert it here. So we end up into having a matrix, a linear system of equations where we know the a, we know the b, where the b is minus f of x, and we need to find this new x, right? Sorry, this new x is the delta x. So then the last step, the final step, it will be to find the new value of x, which will be xi plus 1 will be equal to xi plus delta x. Okay, so this is how we are going to solve the system. Okay? So these are all the steps that we need to use. If you remember, in the Newton-Raphson method, now this is Newton-Raphson method, but using vector notation. In the Newton-Raphson method, we had the following. We had xi plus 1 was always equal to xi minus the function evaluated at xi over the derivative of the function evaluated at xi, right? So this is Newton-Raphson, this was Newton-Raphson for a single value. And now how many steps we would use if this was the Newton-Raphson method? The first step, it used to be like this. We assume an x0, right? The second step, we find that the delta x is equal to, what is delta x? It's minus f of x0 divided by the derivative of x0. Probably I'm a little too far. Then the third step, it's simply x0 plus delta x. This would be the new value, right? So this is what we have done so far in the Newton-Raphson method. Now we have a vector. Newton-Raphson method is changing a little bit, but more than difficult, it's really a nice exercise to work with. So let's have a look now. Let's erase this and let's go back to the example that we had. So we have this example, and the first thing that we need to do is we need to find the Jacobi matrix. Now, what is the Jacobi matrix? This is this matrix. It is the derivative of the first function with respect to x, which is 2x, and the derivative of the first function with respect to y.
Profesor, më fal.
Po.
Është shumë e paqartë pamja, nuk e di, mund ta rregulloni pak se nuk duket fare.
Patjetër, ka për reflektim nga ju faleminderit për komentet. Sa shikoj mos ka një koment tjetër me shkrim. Po. Është shumë e paqartë pamja. Po pse është e paqartë? Një sekondë. Let me check the settings if the settings are the video is okay, so this is good. Po është e paqartë pamja në gjithë rastën apo vetëm aty ku po shkruajmë tani?
Në të gjithë rastën.
Po si ka mundsi? Prit atëherë të ashtu. Është nga Wi-Fi. Po mund të jetë Wi-Fi im apo Wi-Fi juaj? Si mund të jetë situata? Mund të jetë Wi-Fi im.
Nuk di nëse kam vetëm unë këtë problem, po.
Atëherë ka mundsi. Atëherë mund të jetë interneti im, por mund të jetë që ka mundsi e vogël, pasi disa po duket mirë. Okej, faleminderit për komentet. Shumë ju faleminderit. Nëse dete qartë, mund të jetë kjo që unë mund ta kem internetin e dobët, por nëse është në rregull, mund të keni ju ndonjë lidhje jo të mirë, dakor? U mendova mos kemi dritën që vjen nga dritarja. So if it is good for some of you, allow me to continue. So the Jacobi matrix, this is how we get it, and then we take the derivative of the second function with respect to this first variable. So sa është derivati y-it me x-it, ky del y. Sa është derivati x-it me y-in, ky del x. Tani lejoni të them diçka. Kjo Jacobi method është thjesht një mundësi për të bërë pak më shumë është një mundësi thjesht për praktikuar pak më shumë the equationin once more. So we are trying to you should not see this, mos e shikoni sikur është shumë vështirë, vetëm mendoni sikur po aplikojmë të hapin edhe një herë ax baraz me b. Edhe pse e përdorim këtë për gjetë delta x-in. Me këtë shembull do mundohemi ta qartësojmë pak. So here we found the Jacobi matrix. So we are following these steps actually, right? But we have not done something. We have not assigned an initial value. Let's assume that x0 is equal to 0.5, 1.5. Let's assume that I have to use the board wisely. Let's assume this is 0.5, 1.5. This is x0. That's good. And then the next step, we need to evaluate. So I think this part is clear. Next step, we need to evaluate the functions at x0. And this function at x0, we need to do the following. We do 0.5 squared plus 1.5 squared minus 3. This is equal to, let me see what this is equal to. I don't have it here, 0.5. don't have the numbers here, but this is something like, allow me just, I thought I had prepared most of the work. So 0.5 squared, we get here 0.5 times 0.5 plus 1.5 times 1.5 minus 3. This is equal to minus 0.5, minus 0.5. And then we have the other function. The second function is equal to 0.5 times 1.5 minus 1. This is equal to 0.5, well, it's easy actually, times 1.5 minus 1. This is minus 0.25. So this is minus 0.25. Now, the next step, so we found this. We found the second value. Then we need to find what is the Jacobi matrix. The Jacobi matrix, this will be equal to 2x. What is 2x? X is 0.5, 2x is 1, 2y is 3, and y is 1.5, and x is 0.5. Okay, so this is the Jacobi matrix, and with this Jacobi matrix, and which is 1, 3, 1.5, and 0.5, we need to, let me think for a moment, minus 0.25. We need to evaluate the delta x. So let me write this. We have 1, 3, 1.5, and 0.5. This is the Jacobi matrix, times the delta x and the delta y. Okay, so this is equal to, so actually we're writing this is equal to minus f of x. Now, what was f of x? It is minus 0.5 with a minus 0.5. This is 0.25. Now, the only extra information that we are including here is that we found the Jacobi matrix in step 3. We found the f in step 2, which these are the values. And in step 4, we are trying to find the delta x, but we write it in this form. So if we try to solve this, we can insert, you can use a small programming code, like using the Gaussian method for solving linear equations. And let's see, probably we can have a look here. Probably, so we can try to reconnect. We can just call this Jacobi matrix J.
Question mark.
This is equal to 1, 3, 1.5, and 0.5. That's the Jacobi matrix. And then on the other side, we have the B vector, which is 0.5 and 0.5 and 0.25. And for this, we can use any one of these functions that we've used before, and we apply it here. This is the Jacobi matrix, that's the B. Apparently the answer, so the delta x, so we found it. So we find that the delta x is equal to, as we see from here, 0.125, 0.125, and the change in delta y is 0.125 again, 0.125 again. So now maybe I need to erase this part of the board.
Profesor, më falë, ato përgjigjet e fx0 nuk ishte me minus?
Po, shumë e drejtë. Faleminderit për ndërhyrjen. Me minus ishin, por këtu
duhet absolute value.
Jo, këtu është minus f of x.
Në rregull, në rregull.
Në rregull, a jeni dakord? Kjo është diçka që jo, shumë për vërejtje me vend është, por këtu kemi shit minus f of x, pra thonë ishte të gjetëm punën, por këtu përgjigjet të bëhen minus dhe marrin
Po, në rregull.
Tani kemi gjetë sa të ndryshojë ky vektori. Dhe vektori normalisht ishte të them diçka të vogël në fakt. Nëse kemi një vektor këtu, I cili, ose ta në ndërtojmë fikse, të vektorin që kishim në fillimisht. Sa ishte vlera fillestare, le të caktojmë 0,5 në pikë 5. Çfarë do të thotë 0,5 në pikë 5? Kemi një njësi këtu 0,5, kemi dhe 1, 2, 3, 3 njësi këtu 1,5. Dhe ky si vektor vetë është këtu, është ky vektori këtu. Të vektorin do ndryshojmë, me sa do ndryshojmë, ne gjetëm që delta x-in do ndryshojmë nga 0,5 të 0,625. Pra ky si vektor do rritet pak, dhe do marrim një vlerë këtu. Dhe y-ni me sa duket do rritet me 0,125, do vi këtu, dhe ky vektori do vi diku këtu. So we're trying, pra delta v-ja është një, we're going to get a new value, which will be like this, right? So we go from the red solution to the blue one, and true ecim. If you allow, if I can continue, so it looks like we started from pse fillon nga 0,5, se kur ndërtojmë grafikun, duket sikur do të jetë një rreth diku aty afër. Normalisht te Gauss Seidel filloshim gjithmonë nga 0,0. Po këtu e nisim që këtu, dhe që këtu pastaj vlera e ardhshme gjetëm delta x-in, i takon të 0,625, 0,625, dhe vlera tjetër është 1,625. Pra, tani kemi të vlerën e re. With this new value, we need again to evaluate the function in here. Okay, so what do we do? Këtu të këto vlerat, bëjmë 0,625, 0,625 plus 1,625, pra vlerat e pak të mëdha, 1,625, minus 3, do dani vlerë e re. Këtu do kemi produktin e këtyre dyave, 0,625 me 1,625, minus 1, do gjemë dhe një vlerë të re këtu. Dhe kur gjemë të vlerën e re, do na dalë, jo ndoshta mund të jeni pak më të shpejtësuar, 0,625 që shundon 0,625 minus 1,625 që shundon 1,625 minus 3, në qoftë se s'kam bërë ndonjë gabim, jo është plus, nuk që ka minus, që ka më plus, më bëra minus, atëherë plus paras 0,03. Del me plus 0,03. Tu vlera tjetër 0,625 që shumëzon 1,625 minus 1 më del 0,016 me plus 0,016. Pra, që gjetëm këtu? Gjetëm të funksionin fx-in. Kur gjetëm të funksionin fx-in, në fakt kur gjetëm të bën të ekuacionin ax baraz në b. Pra, kjo është 0,03, dhe ndryshojmë shenjën se është minus fx, dhe çfarë do na dalë minus 0,03 minus 0,016. Tani, do vlerësojmë dhe këtë matricën e Jacobit me këto vlerat e reja, që do thotë 2x. Pra, dhe t'jurëm të dyja, kjo ishte Jacobi Matrix herën e parë. Herën e dytë, kjo do dalë 2x 2,625, 0,625 që shumëton 2, 1,25. 2y është 1,625, 1,625, shumëzim për 2, 3,25. Dhe pastaj kemi edhe x y-ni, pra këto nuk dyshojmë. Këtu vendosim y-nin 1,625 dhe x-i është 0,625, 0,625. Pra këtu kemi këto vlerat për të bërë diçka, atëherë unë po shikoj diçka këtu të you'll be looking at me, por që mos të ndroj ekranin 2-3 herë. Unë thjesht just gonna run the same thing. So Jacobi Matrix is 1.25, 1.25, 3.25, 3.25, then we have 1.625 and 0.625, 0.625. This is this, and the b is equal to the answer vector that we wrote here together. This was minus 0.03, and I hope that these values were close to the true ones, minus 0.03. Minus 0.03 and minus 0.015. minus 0.0156. Then we apply again. So I found, using this little thing that is written here, that the new delta x, so this was the first delta x, the new one, I'm reading it from here, it's 0.007 minus 0.0, how many zeros? 07. And the other delta x is equal to minus 0.0065, minus 0.0065. Okay, so I needed to read this, so that's why I needed to read my screen. So it looks like initially we found the delta x in the first step, it was this. Okay, so this vector in red, we tried to draw it together, but for sure it's not to scale. Then we found this vector which is now in blue. Now the next delta x, the next change in the values of x is this. Okay, which looks like is 7 times 10 to the power minus 3. It's relatively small, which looks like we are really very close to finding the exact solution, the exact answer. Okay, and so it looks like the values, if we change by this much, they are approximately, if you take out 0.07, let me see if you can see the top part of the board. So the next step is 0.618, and if you remove 0.065, this is 1.618, something like that. Okay, so this is how we are approaching to this again. So this is how I just want to present something here on the screen, and I'm going to share with you this the codes that I use in the classroom. So this is something we can write regarding the Newton-Raphson 2. So this is Newton-Raphson, which uses the Jacobi matrices, or Newton, which solves even nonlinear equations. And let's define here the function f of 1. So this function, if you can, I think you can see my whole screen. So the function that we show here, we're dealing with a vector. The first function is x1 squared plus x2 squared minus 3. That's the one that we had on the board. And the second function is x1 plus times x2 minus 1. That's the second function. So we save this. And we look at the Newton-Raphson 2. We just need to write, let's copy this part. Sorry.
Question mark.
So we get this here, and
question mark.
so we have to evaluate this
Question
function
mark.
function 1. Yes, that's correct. We have to, let's forget the tolerance, and let's assume that the initial value that we're going to insert is 0.5 and 1.5, the same way that we showed it here on the board. 0.5 and 1.5. Okay, undefined. No, that's wrong. I copy pasted it from there, but this is Newton.
Question mark.
We spell this one Raphson 2. Okay, so it looks like the root here, it's 0.18 and 1.618. So whatever we found on the board, this is what we find. Again, you can, for any exercise or for any homework that I might assign, you can use these codes. And let's look at a different function. Let's assume that we have a function, let me see. And probably, let's see actually how fast this converges. It's not that non-linear, but let's see at the code where is too many iterations. I think the iterations that are made here, and I think I can plot here I. So I'm not sure if I'll be able to show this, but let's see. So we want the output. Let's try to see how many steps we will need. So let's output here also the I. Okay, so we need 5 steps to get to this convergence. On the board, we just did 2, and we were pretty close to this. But let's see if we make this value 1. We need 6 steps. Okay, so apparently we need 6 steps if we start from a different value. But actually, let's do this one 1.5 and this 1.5. And apparently there is something wrong. Matrix singular to machine precision. Oh, okay, we have a problem here. And what could be the problem is that I cannot identify this, but can you go over this one and see why we get this machine precision? So it looks like the solution is 1.18 and 1.18, which if we look at the PowerPoint, this doesn't make much sense because the figure, it would be this. So the roots is telling us some value around here. No, it doesn't make sense, but let's also try to find x 1.5 and y 0.5. Now we find, if you look, the previous root is this 0.6 and 1.6. Okay, so it's this part of the figure 0.6 and 1.6. We are here. Now that we gave a different starting point and 1.5 and 0.5, we are getting this other root, this one here. Okay, but it takes 5 iteration steps for us to. And meanwhile, we can even try to do this one with a tolerance level. We can exaggerate a little bit. Oh, it was faster. Okay, oh, maybe the default is much smaller than what we provided. Okay, it took one more step and it gave a tolerance level 10 to the power minus 8 or minus 9, which is pretty good. So Newton-Raphson are fast conversion techniques, and it looks also for these nonlinear functions or nonlinear systems. So assume that you go to a different class and you are given several functions. You need to find the root. This is really a good method. Let's see this other example. And by the way, let's see actually. So we are outputting also how many times it takes. So let's make this minus and let's make this other minus. So we'll try to find, yeah, we found this other root which are beyond the 0. Okay, so we are around here, which is okay. Now, let's go back to the what is this hold? To quit. I don't want to quit. No. Okay. Am dëgjoni dot? Mund të më konfirmoni pak? Can you hear me?
Po.
Okay, besoj e shikoni edhe ekranin tim, po unë s'po kuptoj çfarë po ndodh këtu. Se duket meku pas një shortcut, so there is a shortcut hold Q. I didn't want to do it, hold to quit. How can you escape? You know, there are these videos on YouTube which has millions of
Po profesor, do të hapësh mikrofonin, se ka hapur më duket.
Okej, më falni, po, e hapa, faleminderit që ashtu më dëgjoni besoj.
Po.
Okay, që ka interesant, mu fi nëse, it was a technical problem, everything was gone, but apparently since you are online, I'm just the personi I 80 që po bashkohem, so I thought I had to restart the whole class, but the whole class is active, which is good. Okay, I apologize for that, but besoj tani që më shikoni kështu në dras, mund të shikoni pak, keni një shembull këtu. You have a new example. So we have a new system of functions. So these functions we have here f1, f2, and f3. So we have these three functions, and all of these functions they are so f1 is a function of x, y, and z, and this is equal to 0. Then we have another function f2, which is again a function of x, y, and z, 0. f3 of x, y, and z, this is also equal to 0. So all of these are nonlinear, right? So they are pretty much let me say, relatively slightly more difficult than the linear system of equations where we use the Gauss Seidel method. And we have nonlinear terms like sine of x, y squared, natural logarithm of z, 3x, 2 to the power y, z cubed, and all of these. And let's say that we want to solve this system. And now, in order to solve this system, let me change a couple of settings, because I really, I think I can improve the slightly. Now, this system, if we solve this one, it will be relatively difficult. But let's see what we have here in the function. So we just need to change the function that we define here. Let's change this. So let's save this. So this is the new function. So this function that was on the board, we see it here, which is now sinusi I x1 plus x2 katror plus logaritmin e x3 që është z-ja, minus 7. Ky është funksioni I parë. Funksioni I dytë është ky tjetri. Dhe funksioni I tretë është x plus y plus z, që ne po e shohim x1, x2, x3, sepse kemi të bëjmë me një vektor. E bëjmë save këtu dhe pastaj mund të bëjmë përsëri Newton-Raphson 2, and the answer for this one will be
Question mark.
okay. Okay, so let's see. We have this new system.
Question mark.
We have to evaluate the function 1, and now we have to insert. Let's try to start. Let's assume, or let's have the x0 for this system that was written on the board as 0, 0, 0, undefined line 1. It says.
Question mark.
Okay, so here we have a problem. This is I1. Line 1, column 13. Okay, no. Can anyone see what is wrong here?
The R at Newton-Raphson probably.
Oh, it's capital R. Okay. Okay. Okay, so we start with the vector 1, 1, 1. Okay, that was the whole thing. What if it's okay? Probably we even can check how this converges by plotting here the number of iterations that we get. We don't see this. Okay, oh why? So it takes 7 steps to converge from 1, 1, 1. Okay. Machine precision. So okay, so we have a 0. Do we have any function which is not defined with 0? We have logarithm is thus that 0 is not defined. So apparently, yes, we have to keep that out. So like you give me logarithm xi by going to Schonvogel. Okay, so we found it, but it's in 11 steps, even starting from the natural logarithm of a very small numbers, which is good. Actually, this is maybe the part that we can really kill it. So in 14 steps, it improves. So let's approach again to the 0. It took less steps. How is it possible? Okay, 13 steps anyway. But so this is how we can use this Newton-Raphson method to solve, to look at non-linear systems. And again, solving AX is equal to B is relatively a piece of cake when compared to this. But this is in principle also not that difficult. So we just had to write down a Jacobi matrix, which was in principle a derivative of all functions with respect to the variables. Now we know in principle how we can generate matrices, which are whenever we have a pair of whenever we have a pair of indices, if we have x, y, this becomes immediately a matrix, right? So in this case, the Jacobi matrix for this system, we take the derivative with respect to x. This is cosine x, right? The derivative of the first function with respect to y is 2y, and the derivative of the first function with respect to z, what is ln z? It's 1 over z. Then the derivative of the second equation with respect to x is 3, 2 to the power y. What is the derivative of 2 to the power y? Do you remember? I don't remember this, but I think it's something like y times 2 to the power y, or... Kush e mban nga kalkuluesi, si e gjeni derivatin e 2 në fuqi y-it?
Do të jetë 2 në fuqi y lënë 2.
Lënë 2 shë? Okej, lënë 2 shë shumëzohet të atyre? Okej. Janë disa teknika që si e ke pas bërë këtë ne kemi pasur që y ishte barabartë 2 fuqi x, marrim lënën 2 karahat, që është barabartë x është shumëzon lënën e 2-shit, po ke drejt, atëherë kështu dhe, po. Marrim derivatin këtu, kjo del diferencialin në të 2 karahat, ti ke të drejt, atëherë ashtu është, por nuk është jo esenca jonë, por pak a shumë i bie që Jacobi Matrix, kështu do e konstruktojmë, dhe të faktu marrim derivatin kësa me x i këtë njësh, ta kemi matricë 3x3 të cilën duhet ta vlerësojmë etj. Tani, so this was most of the material regarding the Gauss Seidel method. Unë mendoj që me Gauss Seidel method mund ta lëmë kaq që do thotë sepse e vetme gjë që na ka ngelur është të zgjidhim pak më shumë ushtrime. Dhe besoj që për pak më shumë ushtrime, edhe ju mund të shikoni, por teknika është komplet e njëjta teknikë. Tani hapi tjetër që ne duam të shikojmë është që kemi dëshirë të kalojmë tek we can start the interpolation. Now interpolation there is, let me see, we have a curve. Yes. Okay, while I talk, let me erase this part. So the next topic, it will be interpolation and curve fitting. Interpolation and curve fitting, there are two concepts which are very close to each other. Okay? And the difference between these two will be shown in a moment. So let's assume that we have a graph, and let's say you are in a class and you are given some data points. Someone is given, let's say, the number of on day 1, on March 10th, the number of people that were affected by coronavirus in Albania. Let's say, so it's a small number. So let it be day 1, and then after a couple of days, the data increase and increase, and who knows, we have some jumps like this, okay? And you are taking numerical analysis, and someone is asking you, okay, you took numerical analysis, show me what is the dependence on the number of infected people in Albania as a function of time, okay? You are taking this course, you should do it. Okay? You should not say, oh, I don't know it, but you can do it. And in order to do this, we can use interpolation. So we can have, let me get another pen. So, in fact, we'll start the course with discussing interpolation, okay? And probably it's best if we discuss for a moment about curve fitting for the sake of the argument, and I'll make it clear why. Now, curve fitting is in red, and the curve fitting would be a function that is assuming, so this one allows errors are accepted. I'll explain in a moment what this is, but interpolation, no error allowed, no error allowed. So the curve fitting, it might be something like this, okay? But interpolation, it wants this. It's jumping from one function to another, okay? So this would be the interpolation. But curve fitting, it tries to draw a general curve, which it does not even have to pass through all of the points. Now, reasonably speaking, this is mostly used, the curve fitting, okay? Because whenever we have some data, if one of the data has some error, this should not force all of our functions to go through the data. Maybe because of the error, coming within some reasonable closeness or closure or proximity, coming to a certain proximity to the specific, so we could have a data point right here, right? Something drops. It's very hard to bring a single function down here for the sake of one data point. So that's why curve fitting is more practical. Now, interpolation, the interpolation, it assumes that we are going to go to each point with presumably smooth functions. We can even connect these functions with straight lines. Okay, let me find a different color. I'm not sure if, so I'm drawing with blue, interpolation between these points with straight lines. Okay, so we can have linear functions, but this is not always the best. Probably the best is to have functions that we can take derivatives. So differentiable functions or smooth functions is the best to have. Okay. Now, what was interpolation? We are given some data points and we try to predict a function which connects this point with this and so on. But this is not all the story. We can also, interpolation also takes care of predicting a function here, and also if we have no data, so let's assume that these are the days when we have data, okay? Now, one can ask the question, okay, you have data, let's assume that we have data for January, March, July, and December. Okay, you have 4 months of the year, you have some data. And somebody is telling to us, okay, you have from July to December, you have only 2 data points. Can you tell me what is going on September? How do we do that? We construct a function which passes through all the data points, and then we look where the projection here falls on a specific value, okay? So again, if you see here, we have a data point here, we have a data point here, we can find a function, we can fit a function going there, but then the best question comes after that, asking, what happens to this point right here? Then, since we have drawn the function, we go up, we look where it intersects, we come this way, and we say that we found the answer, okay? So this is what interpolation takes care. Now, regarding the interpolation, there are different techniques that can be used, and these different techniques, for the sake of, since nowadays we use a lot of computation, it is always best to have a technique to find the interpolating function. Okay, so all the question is to find a function that goes through the data points, and then, but we want to do this in an efficient way. So we don't want to spend too much time running a computer, or we don't want to spend too much computational time. For this reason, the best techniques nowadays are also the techniques that converge fast. Okay, so we might be given a large data set, and then you run it on a computer. It might take minutes, seconds, or even hours, and sometimes even days. Because sometimes the dimensionality of our data set can be huge. So we can have data sets 30 by 30 by 30. Okay? So we can have a huge number of data. So it's way more complex than having y is equal to x, as we have here on the board. So for this reason, I can repeat my argument again. Figuring out the technique that converges the fastest is also the best one to use, or it's really important. So regarding this, I think we can start with a couple of techniques that we can use for interpolation, and one of them is in fact Lagrange method. So Lagrange method, what it finds, it generates, so it's a polynomial interpolation. Now let me say, Polinomet janë funksionet më të mira që neve na pëlqen të punojmë me polinomet, për faktin se polinomet kanë këtë formë. Janë këtë formë x fuqi n. So we sum over an times xn, where n goes from 0 to infinity, or we can stop somewhere. Okay, so let's say some capital N. Let's not go to infinity, because if we go to infinity, that means that we are including, për shembull, po e lartë të infinit, kjo do të thotë që përfshim edhe funksione që nuk janë polinome, për faktin se edhe n fuqi x, edhe ln-ja e x-it, edhe sinusi i x-it mund të shprehen si shumatore me polinome. Për shembull, ne dimë si ta marrim Taylor series expansion të sinusit, i cili është një funksion. Sa herë për shembull ti pyesuni juve, sa herë mund të marrim derivatin nga sinusi? How many times can we take the derivative of sine? Kush mund përgjigjet? Pa fund, shumë e drejtë. So we can have an infinite number of derivatives. So we can take an infinite number of derivatives out of sine, okay? But if we have a polynomial, nëse polinomi është i gradës së 10, sa derivate marrim këtu? 10 herë. Po të kemi polinomi i gradës 3, derivati marrim 3 herë, shumë 3x katror plus 2x plus 7. Derivati i parë është 6x, derivati i dytë është 6, derivati i tretë është 0. So apparently, let me check. So if you have a polynomial of nth degree, we can take n plus 1 derivative, okay? That's good. But now, I should do them to in principle, this is an. In principle, working with polynomials, it's good because we can easily integrate over those. We can easily take derivatives, okay? So often, if we can produce functions, or if we have systems whose solutions are polynomials, that's really good, okay? Now, in the theory of polynomials, there is a very wide area of research, and researchers have been able to find polynomials that are even, that can be generated using recursive relationships, which means that we can start from a polynomial of 0th degree, like 1, then we can get the polynomial of first order, like x, then we can get the polynomial of second order, like 2x squared plus 1, so we can start with 1x, 2x squared plus 1, 3x squared over 2 plus 2x minus 1. So there is a set of polynomials that goes like this, and they are even orthogonal. Now, having orthogonal polynomials, it's something that you might forget, but you can also remember the following. If we integrate sine and cosine, they are orthogonal functions with respect to each other if we integrate them over a specific range. Po të marrim integralin e sinus që shënton kosinus nga minus pia te pia e te 0. Po të marrim funksion sinus që ka frekuencën 10 Hz, një funksion tjetër sinus që ka frekuencën 13 Hz, po të shumësojmë të dy funksione, të dyja sinuse, dhe po të integrojmë brenda nga minus pia te pia edhe kjo te 0. Këtë mund ta quajmë si orthogonality of the functions. Edhe këto polinome të cilët nuk i gjenerojmë shumë, edhe ato mund të jenë orthogonal. Dhe shpesh këto lloj polinome është të bukura, ato janë dhe zgjidhje të shumë ekuacione diferenciale shumë komplekse, etj. Por, gjithë kjo pjesë që na intereson neve, punosh me polinome është mirë, por polinomi nuk është gjithmonë funksioni më i bukur i mundshëm, sepse të detyron që të përdorësh një polinom të një grade shumë të lartë. Argumenti për këtë është ky. Ta fillojmë thjesht. Nëse kemi dy pika, cili është polinomi i gradës më të ulët që kalon përmes dy pikave? Është një polinom linear. Është y varet me mx plus b. Dakor? Right, if we have 2 points, we can find the linear function that passes over there. Nëse kemi 3 pika, çfarë polinomi kalon midis 3 pikave? Një polinom i gradës 2 mund të kalojë midis 3 pikave. Mund ta përdor këto atë. Pra, if we have 3 points, we need a polynomial of p2 of x. Okay? Pra, mund të jetë një ushtrim shumë i thjeshtë. Jepet 3 pika, gjej një polinom, një funksion që kalon midis këtyre 3 pikave, është një polinom i gradës 2. If we have 4 points, we need a polynomial of degree of third, which means that if we have n points, we can find a polynomial of n-1 degree. Pra, nëse ne kemi 20 të dhëna, imagjinoni për një moment, shkoni në klasë dhe profesori jep 20 të dhëna, dhe thot, find a function that fits this, or find a function that describes all of these 20 data points. You need a polynomial of the 19th order. But what does 19th order means? This means this, that we can have 3x to the power 19 plus 4x to the power 17 and so on. But now imagine for a moment, nëse keni vlerë x që është 100, fuqi të 19 është numër shumë i lartë, që do të thotë është pak problematike, pra ne nuk i pëlqejnë polinomet e i grade shumë të lartë për të bërë interpolation. Dakor? Pra janë ca gjëra që duhet i keni pak parasysh, ose disa elementë vegjël që duhet i mendoni shpesh kur mendojmë për interpolation apo curve fitting. Por këtë pjesën që për gjetur the order, një sekond. Tani, ju keni të drejtë për sa i përket leksionit, ne zgjatëm pak sot. Mund ta bëjmë kështu. I can record a series of the class and you can watch the recording later. Plus edhe është mirë të ndalojmë fakt sepse u bë goxha kohë që po incizojmë, mirë është të ndalojmë dikur. Unë falenderoj kush e bëri të komentin këtu, Nathanael, faleminderit që for the organization. Dhe